Hello friends, welcome back. Let us continue our discussion on UV visible spectrometry. In today's session, we will talk about the deviations from Beard-Lambert law in terms of what are the deviations and what are the factors which cause these deviations from the basic observation of the law. The session is planned as follows, that is, to begin with, we will review the contents of the previous session. Thereafter, we will briefly recall what is Beard-Lambert law. Having done that, we will come down to the main theme of today's session, that is the deviations from Beard-Lambert law. These deviations will be covered up in three broad categories. They happen to be the real deviations and chemical deviations, and then we will talk about the instrumental deviations. Towards the end, we will sum up what we do in today's session. Okay, let us move further. Let us move further and see that in the previous session, what we did, we basically started by differentiating between three very closely related terms and very important terms in spectrometry. They happen to be spectroscopy, spectrometry and spectrophotometry, because these terms are really very important to be understood. Having done that, we talked about the basic principle of UV visible spectrometry, and in this context we came down to the Lambert law, Beer law and Beard-Lambert law, and towards the end we talked about some applications of the Beard-Lambert law. That is what we did in the previous session. Okay, let us move for today's session. Let us briefly recall what is Beard-Lambert law. You will remember from the previous session that the Beard-Lambert law basically is a law which relates the attenuation of incident radiation with concentration and the path length of the medium. Let us see, understand this. Basically what we have is, suppose I have a cuvette, a container here which contains the absorbing species at a concentration C, and this container has a thickness of B. Now, if to this container, if I pass a radiation of intensity P naught, what comes out is P. So, this how much of decrease has happened? How is that decrease related to the concentration and the thickness of the medium? That is basically Beard-Lambert law. You will remember that mathematically this law is put as follows, that is log of P naught by P is equal to A, that is absorbance, equal to ABC or epsilon BC. And you remember that we defined all these terms in the previous session, that is A is called as absorbance, which we will be using very often there, and then this small a happens to be absorptivity of the absorbing species. B is the thickness of the medium, as I told before. C is the concentration of absorbing species there, which were taken in the cuvette, and epsilon happens to be the molar absorptivity. Okay. So, that is about Beard-Lambert law. Now, if this be the law, what do we expect? We expect that since this expression happens to be a linear expression, which means that absorbance A is proportional directly to B, the thickness of the medium, and C, the concentration of the absorbing species. Epsilon is molar absorptivity, that is the proportionality constant. Now, if I take B to be constant, then this epsilon B becomes a constant. In other words, we can say that at constant B, I expect a plot between A, that is absorbance, and C should be a straight line passing through the origin there. So, that is what I expect from Beard-Lambert law. What does it mean is that if a system is following Beard-Lambert law, then I must get this kind of a straight line plot. Okay. But when we do actual experimentation, we find that in many cases there are certain deviations, and the deviations could be either the positive deviations, that is the observed absorbance happens to be more than what is expected from the Beard-Lambert law there, or sometimes what we observe is that there are negative deviations, that is the absorbance happens to be lesser than the expected one. So, these are the typical kind of deviations we come through, and these deviations are normally observed at little higher concentrations. We will talk about all the factors as we move further. Now, if I just see what are different types of deviations we have, we can put the deviations from Beard-Lambert law in terms of three categories based on the factors responsible for that. The first one typically is called as the real deviations, or they are also called as the limitations of the law. And the second category happens to be the chemical deviations, and the third one is instrumental deviations. We will talk about each one of them one by one. Okay. Let us begin with the real deviations or the limitations of the law. The real deviations basically are fundamental deviations, and they arise because of two factors, and they happen to be high concentration of analyte or the presence of electrolyte. Let us see what happens in these cases there. Okay. Now, what we observe is that in typical measurements, if the concentration of analyte happens to be less than or equal to about 0.01 molar, that is just an indicative number, it is not that absolutely 0.01 onwards things will change, no, it is just an indicative number there. That is, at concentrations less than or equal to 0.01 molar, we find that this law holds true for most of the cases we can make true. That is, if I start from here, say 0 concentration to about 0.01, I find that is a straight line coming over there, that is my absorbance is increasing linearly with the concentration there. And this basically happens is that at such low concentrations, so this is sample I have shown here, a potassium permanganate there, we find that the analyte species are quite sparse, that means they are distributed, they are away from each other, and there is not much of an interaction expected between the absorbing species there. But when the concentration increases, say at concentrations greater than 0.01 molar, that is again I am repeating, it is an indicative number there. What you find it at high concentration is the same KMnO4 at higher concentration, we find that there are much larger number of absorbing species there. So, since the number of absorbing species are increased, so that leads to some kind of a interaction between them. That means, there is one species there initially at low concentration, we had a species here, they were randomly distributed away from each other. At high concentration, the species come too close to each other. When they are too close to each other, then they start influencing one another. As a consequence, what happens is that the charge distribution, suppose this is one species here, the second species was far enough, nothing was happening there, but that come too close there, then the charge distribution around this absorbing species can get altered, and that can be manifested in terms of the change into the absorbance there, absorbance will become less there. So, what you see is that up to about 0.01 molar, we find that there is a linearity in the graph there. At higher concentration, there is a negative deviation as shown in this particular case. Another possibility is that when the analyte concentration is high, the second one possibility is that the species are interacting with each other. Second is the refractive index of the medium per se changes, and that also can lead to changes in the absorbance, and as a consequence there is a deviation from the linearity as expected from the Lambert law. That is as regards the concentration of the analyte goes. The second factor for real deviation, and that happens to be the presence of electrolytes. Electrolyte basically is that typically suppose I have a solution. In a solution I have put some organic molecule which I want to look into. Now that organic molecule is in a solution, means there are solvent molecules, and also there could be some electrolytes in that. There are simple not a lot of systems there wherein the electrolytes are part and parcel of the absorbing species or the medium which we are using for measurement there. Okay. Now in such cases what happens? What happens is if electrolyte is at low concentration, typically we find that the law is observed fairly well. But when the concentration of electrolyte increases, then what happens is that earlier we talked about the species interacting themselves, that means there is one absorbing species, second one, two are interacting. Now what we are talking about is there is one species here and there are electrolytes around there, and these electrolytes in low concentration do not influence it much, but when the concentration of electrolyte happens to be more or larger one, then even this electrolyte can influence the behavior of the absorbing species, and that leads to the deviations from the law. So, primarily there are two factors, one is the concentration of analyte and second happens to be concentration of electrolyte, which is not an absorbing species, it is just which is in the presence in the medium, and that actually influences the absorbing species over there. Okay. So, this actually influences in terms of causing some kind of a deviation because of the deformation of the molecule which is absorbing species there. What we observe is that if I am using a high electrolyte concentration, then even for the low analyte concentration, because we said in the first factor there, that is when the concentration of analyte is less, then the law is observed. But even if for low concentration of analyte, if the electrolyte happens to be in high concentration, that also can lead to deviations there. So, one has to be careful about whenever I am trying to design an experiment or making measurements, we have to ensure that these factors are taken care of. Otherwise, what we expect from the Beer-Lambert law, that will not be observed. Okay. Let us go further and talk about the second type of deviations. They are the chemical deviations, as the name suggests. So, these are deviations which are arising out of some change in the chemical nature of the analyte there. Okay. There are different ways this can happen there, and they happen to be one typical observation what we have is, that is the hydrogen ion concentration. Hydrogen ion is a very common factor which causes chemical deviations from the Beer-Lambert law. And second possibility is that suppose you have analytes, if there is an association of analytes or there is a dissociation, there is one analyte which breaks down into a larger number of analytes there, then again there could be deviations there, or there is a complex formation. So, all these can lead to the change in the chemical nature of absorbing species, and as a consequence there are deviations from the law. Okay, let us take up some examples here. Let us talk about the first case first, that is of hydrogen ion concentration. Hydrogen ion concentration typically influences the ionic state of the absorbing species there. Let's take this example there. The example happens to be that of the equilibrium between chromate ion, dichromate ion in aqueous solutions of potassium dichromate. Essentially what happens is, let us take look at this picture here. If I take potassium dichromate solution or even take chromate ion solution there, now if I change the pH there, suppose I have chromate ions are yellow colored, that is a solution of chromate ion shown there. If I add some acid to that, as the concentration of hydrogen ion increases, the color of the solution changes from yellowish to orangish kind of color there, and this is because of the presence of dichromate ion there. That means there is a change in the absorbing species there. We can even see here that the chromate ion has a lambda max of about 375 nanometers, whereas dichromate ion absorbs around 350 and 450 nanometers there. That means there is a change in the composition of the absorbing medium over there. Okay. So, what happens in this case? What happens is, if I want to make a measurement of the concentration say of chromate ions or of dichromate ions in a given solution, I have to be very careful about the pH of the solution there, because if the pH is not maintained properly, then what happens is, if I want to measure this one and there is excess of certain hydrogen ions there, I will find that part of the chromate ions which I want to make measurement of, that gets converted into dichromate ions there, and there is an error in the measurement there. Similarly, if I want to kind of measure the concentration of dichromate ions and there is a change in the pH because of this hydrogen ion concentration, I may convert this dichromate ions to chromate ions. So, as a consequence, the measurement again will be erroneous there. Okay. So, the message from this is that whenever I am making a measurement of systems which are sensitive to hydrogen ion concentration, I must maintain the pH properly. If I do not maintain pH, then the outcome of my measurement is going to be not in order there, which is not a reliable output over there. Okay. Let us go further and talk about yet another example, say bromothiamyl blue. It is a typical common indicator there, and if you just see it here, this picture shows the pH dependence of the color of this indicator there. We find that in acidic medium is very faintly yellow colored there. As that the pH is increasing, becoming alkaline, we find that it turns to blue color there. Okay. Now, let us look at the spectra of bromothiamyl blue at different pH values there. What you find is that this green spectrum here, this is the spectrum of bromothiamyl blue in the acidic form, that is, this is the acidic form of the indicator there, and this red spectrum here represents the basic form of the indicator there, and that this basic form here we find that there is a some kind of a quinoid structure there, and because of this quinoid structure there is a large absorption at this particular wavelength over there. So, the message from this spectrum is that the spectra of the acidic form and the basic form happen to be glaringly different from each other. Okay. Now, what happens is, as we increase the pH, we saw that as we have low pH, the medium is acidic, and this species is the predominant species there, and spectrum happens to be this. As I increase the pH, so this species gets converted into the basic form there. As a consequence, the intensity here, that is the absorbance here, decreases, but and that of this part here, which is more of the basic form, that increases there. So, this goes on decreasing with the increase in the pH, and this band goes on increasing there. So, we find that there is a kind of an equilibrium between the two forms there. In such cases, in some of this happens to be one of the examples there may be a certain wavelength. Say in this case, this happens to be about 501 nanometer. At this wavelength, molar absorptivity of the acidic form and the basic form happens to be same. So, that means at this point the absorbance does not change with the medium. That means you take any pH, this absorbance does not change. So, and such a point is referred to as isosbestic point there. This is a very characteristic point for certain systems where there is an equilibrium between two forms of the same absorbing species there. And normally it is recommended that if I want to make a quantitative measurement there, then this wavelength should not be used to make the measurement there. We can use this maxima there or this maxima to kind of quantify the acidic form or the basic form, as the case may be. Okay. Let us go further. Let us go further and talk about the another possibility whereby there could be a chemical deviations from the Beard-Lambert law, and that possibility happens to be, say, complexation. Association or dissociation, other possibilities there, but I am taking an example of a complexation case there, wherein the original absorbing species and the one which comes as a consequence of complexation, they absorb differently there. And as a consequence, that leads to the deviations from the expected Beard-Lambert law behavior there. And let us take this example there. This is cobalt chloride ion equilibrium in aqueous medium there. If I take this is aqueous solution of cobalt ions there, and cobalt ions will be in hexaaqua form there. So, this is a kind of a pink colored solution there. But if to this solution, if I add chloride ions in some way, so what happens is these chloride ions kind of get into a complex formation with the cobalt, and these water molecules are thrown out there, and what you get is this following species there, which is a complex ion there, and which happens to have a blue color there. So, what you find is that in this case, if I am trying to make a measurement of cobalt. So, if I take cobalt and just make measurement in the absence of chloride ions, I get certain concentration there. But if the solution happens to have certain amount of chloride ions there, then what will happen is these chloride ions will convert part of the cobalt ions to the complex there. As a consequence, the color will change, and the particular species which I was measuring earlier at this particular whatever the wavelength be, so that will get altered there. So, there will be deviations from the expected value of the absorbance over there. So, that is another possibility. You can we can take up examples of association or dissociation as well, wherein a given analyte dissociates or associate together to give me new species there, which absorb differently from the original species there. So, these are the reasons for chemical deviations. pH is very predominant one, and even these are very significant. Okay. Now, let us move further and talk about yet another class of deviations from the Beard-Lambert law, and they happen to be instrumental deviations. If you really ask me, these are deviations not only because of instrumentation involved, but broadly speaking the way we conduct the experiment, that means the way we make measurement there. And in this category we can talk about different factors there. One of them happens to be non-monochromatic nature of radiation, second happens to be the stray light, the third is mismatched cells, and the fourth one happens to be temperature. Let us talk about each one of them one by one. Okay. First, let us talk about the non-monochromatic nature of the radiation which I am going to use for making measurement there. If you really ask, Beard-Lambert law or Beer's law is applicable only for monochromatic light. That means, if I have a sample here and radiation is coming, and then this is intensity P naught, and what comes out is P intensity there. So, the relationship between P naught and P will hold together only if this radiation which I am talking about happens to be monochromatic, means of a given wavelength only. But if it so happens that I have this is my absorbing species there, but the radiation which are coming are polychromatic, that means there are a lot of radiations of different wavelengths passing simultaneously through the medium, in that case we find that the law does not hold together. That is what I meant here. That means this is a container having my material, absorbing species there, and this is my monochromatic radiation. It is a depictive one here. But what typically can happen is, if I am not using a instrument which is of a sophisticated one, then it may have radiation which are coming, which are kind of polychromatic, or maybe more than one radiation is coming, or there is a band which is coming and falling onto the absorbing species there. In such cases, there will be deviations there. Let us see why do these deviations come into play. Now, what happens is, if there are radiations of different wavelength which are coming and falling onto the absorbing species, and this is just a indicative spectrum over there. Suppose this is the spectrum of the absorbing species, and let us say there are two wavelengths which are passing through that. One is say at lambda 1, second happens to be lambda 2. Now, for this particular absorbing species, say at lambda 1 absorbance happens to be A prime, at lambda 2 it happens to be A double prime. That means at two very closely related wavelengths we find that the absorbance values are fairly different over there. So what happens as a consequence is that, if you recall from our Beard-Lambert law, if you just arrange differently, A prime is the absorbance at lambda 1, that happens to be log of P naught prime by P prime is equal to epsilon prime B c. If I rearrange that, I can say that P prime to be equal to P naught prime 10 to the power minus epsilon prime B c, and similarly for P double prime over there. P prime is the intensity of radiation which is coming at wavelength lambda 1, P double prime is that at lambda 2. Now, if this be so, suppose I am just taking example of two radiations there, suppose there are many of them, so each one of them will have its own P values there, P prime, P double prime, P triple prime, and so on and so forth. And what actually we observe, the measured absorbance, that actually will depend on the absorptivities of all these wavelengths which are passing through the medium there. Okay. Now, that actually if I have only two wavelengths, let us see what happens there. For if there are only two wavelengths, as I just took lambda 1 and say lambda 2, suppose they happen to be very close to each other. For such a case, the observed value of absorbance will be given by the following expression there. And what it means is that if these two wavelengths happen to be identical, let us take an assumption there, in that case epsilon prime to be equal to epsilon double prime. That means I will observe this straight line, that means the Beard-Lambert law will be observed. But if it so happens that the two wavelengths which are passing through the medium, they happen to have different epsilon values there. Say epsilon prime, that is at lambda 1, happens to be greater than epsilon double prime, that is at lambda 2. So, in such a case we find that the observed absorbance value will be lower than what is expected over there. And if this epsilon prime happens to be far greater than E double prime, epsilon double prime, in that case I will find that there is a still larger deviation there. So, this deviation is coming because the radiation which is passing through has different components, and each component has got different value of absorptivity there. Okay. This leads us to a very important question which we actually make use of, very important observation we keep in mind while making a measurement using spectrometry or spectrophotometry, is that we always make measurements at lambda max values there. Now, suppose I am trying to analyze an analyte whose spectrum is given over here. So, the question is, which wavelength shall I use to make the measurement? I can use this wavelength, I can use this wavelength, I can use any wavelength in principle, but from experimentation point of view, it is recommended that we make a measurements at lambda max, that is somewhere here. The reason for that is, if I suppose I am taking, this is my lambda max there, and if it so happens that my instrument is not providing me the monochromatic radiation, monochromatic means I had to have radiation of only this particular wavelength. But if suppose I need a wavelength of say 100 units there, and if it happens to be say 99 or 101, suppose there is a spread of three wavelengths there, 99, 100 and 101, we find that the absorptivities at these three wavelengths are not much different there. As against that, suppose I had 109 here and 110 here, so the two will differ significantly there. So, what is recommended that for all measurements of using UV visible spectrometry to make quantification of analyte, we must use the lambda max values. Let us go further and talk about the stray radiation. Stray radiation basically is a radiation which is outside the chosen wavelength range for the determination. What it means is the following. That is, suppose I want to make a measurement say from 300 nanometers to about 380 nanometers. So, this is my range which I want to make measurement of. But what can happen is that in the instrument there is a lot of optics involved in that. As a consequence, there could be some radiations which are outside this range of 300 to 380 nanometers, and that could be because of the scattering or reflection from different components of the instrument over there. So, these radiations also cause deviation in the same way as we had in case of a polychromatic radiation, that means when the radiation was not monochromatic. So, essentially what happens is these stray radiations also have certain absorptivity. As a consequence, the observed absorbance values will be different from what I expect from the system over there. So, there will be deviations similar to what we had in case of polychromatic radiation there. Okay. Let us go further and talk about another way we conduct our experiment, that is called as a mismatched cell or qubits. Suppose if that happens to be so, this is one of the operative part here. Typically what we do is we use a set of qubits there. That means, and nowadays we have got quartz qubits available there which are matched. A matched set of qubits means that two qubits I am using, they have got exactly same path length and also have got exactly the same material over there. So, as a consequence, they have got identical absorption properties there. But it may so happen that if I am not using a very expensive or very sophisticated set of qubits, it may have that the two qubits, they have slightly different path lengths. Say one happens to have say a path length of 1 centimeter, the other one can happen to have a path length of say 1.001 centimeter. Even that slight difference also is going to lead to deviations there. So, in such cases we have to ensure that we are using matched cell there. If there is the cells are not matched properly, what you observe is that there could be some kind of a intercept coming into the graph over there, because you remember that Beard-Lambert law typically this curve between A and C, absorbance and concentration curve, must pass through 0 there. So, it may happen that when you got the qubits which are not matched, and so you may have an intercept here or maybe have intercept over there. So, there could be intercepts there. So, this actually is yet another kind of deviations we observe because of the way we are conducting our experiment over there. And this problem can be taken care of by two possible ways, that is, to make number of measurements and do some kind of a regression analysis to take out or to eliminate that error because of the mismatching there. Or more commonly used way out is that we use same qubit for the reference as well as the sample there. That means we use only one qubit first for the reference material, then for the sample over there, and then subtract the reference from the sample. We will talk more about it in the next session when we talk about the instrumentation part. Okay. Let us go further and talk about the last factor we have in mind about the instrumental factors there, that happens to be temperature. Temperature actually is not a very significant factor, because most of the times we make measurements at room temperature. So, it does not vary much course of measurement there, and so we do not expect too much of deviations in such cases. But however, if it so happens that there are certain changes in the temperature, there can be small variations coming over there, and these deviations actually are indirect deviations which may be because of some kind of changes in the ionic equilibrium which is taking place in the absorbing species there, or the medium I am trying to make use of over there. One example I can quote over here is that is of the acidic ferric chloride. If I take a solution of acidic ferric chloride, this happens to be yellow to begin with. If somehow the temperature changes, temperature increases, that means we heat the system, we find that the color changes from yellow to reddish brown. So, since the color has changed, that means the spectrum has changed. So, absorption characteristics will change and the values will get deviated from the expected values over there. Okay. Now, let us sum up what we have done today. What we have done today is we briefly reviewed the contents of the previous session. Thereafter, having recalled what is Beard-Lambert law, we explained the real deviations or the limitations of the Beard-Lambert law. In this context, we talked about the two main factors there. One is the concentration of analyte, and second happened to be the concentration of the electrolyte in the absorbing medium there. Then we discussed different possibilities of chemical deviations for the Beard-Lambert law. In this context, we focus attention on to the hydrogen ion concentration and also the complexation, association or dissociation of analyte and things like that. And then towards the end, we basically described the instrumental deviations, that is the deviations from the Beard-Lambert law as a consequence of the way we make a measurements, the tools we use for measurement, that is the instrument used there or the kind of qubits we are using for that, and so on and so forth. In the next session, we will talk about the instrumentation required for making measurements in UV visible spectrometry there. Thank you.